Hi everyone. So we're going to work on Workbook 2.3. So make sure you have your notebook out and I'm going to start a new page here. Workbook 2.3. All right. So simplifying radicals. So we've been doing a lot of work with radicals and exponents. So expressions that contain radicals can often be written in different ways. You have experience rewriting these expressions using rational exponents, but sometimes radical expressions can be simplified. All right. So perfect squares are integers that are squared. This means the square root of a perfect square is an integer too. For example, 25 is a perfect square because 5 squared equals 25, and the square root of 25 equals 5. However, not all roots contain perfect squares. For example, 50 is not a perfect square because there's no integer that when multiplied by itself equals 50. This means that square root of 50 cannot be written as a whole number. One of the properties of radical exponents is when radicals have the same index and are being multiplied, you can multiply the numbers under the radicals. For example, the square root of 8 times the square root of 7, multiply the numbers under the radical symbol, it becomes the square root of 56. So those two numbers are the same. This means radical expressions can also be broken up into their factors. So if you can multiply them, you can also break them up. So like 15 is the same as the square root of 5 over the square root of 3, and you can pull them apart like this too. So that's something that's really important to know. This is useful when the number under the radical symbol is not a perfect square, but has a factor that's a perfect square. So for example, consider the square root of 50. The number 50 is not a perfect square. However, the factors of 50 are 25 and 2, and 25 is a perfect square. Okay, so we're going to write this one in our notes, the square root of 50. So go ahead and write this down and do this with me. So what you can do is you can break it up inside here as 25 times 2. And then you can actually break the radical. So the square root of 25 times the square root of 2. So these are all okay steps to do. Then you know the square root of 25 was a perfect square. We just talked about that. The square root of 25 is 5. And now we still have this square root of 2. So we've simplified the square root of 50 into 5 times the square root of 2. So that's what they're talking about in simplifying radicals. Okay, so they did that same thing. So here's another example, the square root of 300. So let's do this one. The square root of 300. So I can break up the square root of 300 to be the square root of 100 times 3. And the reason I chose that is because 100, here, let's break this up, actually break the radical. So the square root of 100 times the square root of 3. And then the square root of 100 is 10. And then we still have the square root of 3 that comes on the end there because that one can't be simplified. Okay, so that's the same thing they just did. Using prime factorization. It may not be obvious that a radical expression contains a factor that is a perfect square, but you can use prime factorization to find the perfect square factors. This method can also help you make sure that you have the expression is simplified completely, as you'll see in the next example. So the square root of 252. So begin breaking down the number inside the radical into its prime factors. It may be helpful to use a factor tree to do this. So here's what they did. They made a factor tree to figure out the prime factorization. When broken down into its prime factors, the square root of 252 is equal to the square root of 2 times 2 times 3 times 3 times 7. So we are going to look for any prime factors that appear twice. Pairs of prime factors are perfect squares because an integer times itself makes a perfect square. So rewrite the pairs as factors, pairs of factors as squares, and place them in their own radicals. So what this means is they have 2 squared like this, 3 squared, and then 7. So you can eliminate the radical and the square root because those are opposite operations. So the square root of 2 squared would just be 2. The square root of 3 squared is just 3, and then you have the square root of 7. So that's what they show here. To simplify that down, you get 6 times the square root of 7. So you only need to do that for numbers that are tricky and you're not sure like what perfect squares are inside of those numbers. All right, let's try another example. So this one says 3 times the square root of 12. So we're going to find the prime factors of 12. This one you might know, that 4 is inside of 12 and the square root of 4 is 2. But what they did here is leave the 3 outside because we're not messing with that. That just is in the front of this expression. And then they broke up the square root of 12. And you can see that there's 2 2's, so that means we're going to be able to eliminate part of this radical. So they rewrote it as 2 squared times 3 under the radical there. Then they actually broke the radical up into the square root of 2 squared and the square root of 3. And then you can simplify. The square root of 2 squared is just 2 because those are opposite operations. 3 times 2 is 6, so you end up with 6 times the square root of 3. All right, so now it's time for you to do some workbook questions. So let me know if you have any questions on what we just talked about.